Hey, welcome! Today, we're diving deep into something pretty cool. The hidden muscles inside the machines all around us. You know, from those giant factory robots to something as simple as the click of a car door lock. We're going to follow the journey from a tiny electrical spark all the way to incredible physical force.
So here's how we'll break it down. First, we'll talk about this idea of a machine's muscles. Then, we'll look at the tiny electrical spark that kicks everything off. From there, we'll see how that little spark can control these massive, powerful gates. After that, we'll compare the two main ways to power movement, fluid versus air. And finally, we'll pull it all together and see the whole chain of command in action.
I mean, really think about it for a second. How does a robot arm, actually move? It's one of those things you see every day, but maybe never question. It's not magic, not at all. It's actually this brilliant chain reaction that turns a teeny tiny electrical signal into pure physical power. Let's peel back the curtain and see exactly how it's done. To get to the bottom of that question, we have to start with the most fundamental part of the whole system, what I like to think of as the muscles of machines. Okay, so the technical term is actuator, and it's really the hero of our story today. The whole idea is incredibly simple at its core. It just takes electricity and turns it into actual physical movement. It's kind of like how your brain sends a little signal to your bicep to make it flex. A machine's computer sends a signal to an actuator. Literally everything starts right here. So, how does that actuator get its marching orders? Well, the most common way is with a little device called a solenoid. You can think of it as an electric switch, but for the physical world. The design is it's beautiful in its simplicity. So when the power is off, there's a little spring that just holds a metal rod or piston in one spot. But the second you send an electric current through that coil of wire, it creates an electromagnet. And that magnetic field, bam, instantly yanks that piston right into the center of the coil with this really satisfying, decisive snap. It's an unbelievably fast and super reliable way to get a tiny little burst of motion. So really, the best way to think of a solenoid isn't as the muscle itself, but more like the finger that flips the mean power switch. It's this tiny, lightning-fast push. And you find these things everywhere. Door locks, printers, you name it. But here's the question, right? How does that tiny little push lead to something that can do serious work? Well, that tiny push from the solenoid, that's the P. Because it's just strong enough to control the real source of power. It's strong enough to open and close what we call the flow gates, or valves. A valve is basically a gatekeeper for pressure. I love this analogy. Think of it like a railway switch. The little solenoid's only job is to flip the lever on the switch, but that simple action redirects a massive, powerful freight train. And in our case, that train is high-pressure oil or air. The solenoid gives the command, but the valve is what directs the real raw power. Now, this is a really critical design choice when you're building a machine. A normally closed valve is your fail-safe. If the power cuts out, the gate slams shut. Think of a safety brake on a roller coaster. You have to apply power to release it. A normally open valve is the total opposite. The gate is always open, and you need to apply power to close it. The choice always comes down to one simple question. If the power dies, what is the absolute safest thing for this machine to do? This chart might look a little technical, but don't let the names throw you off. It's just describing how many paths the air or fluid can take. A two-way valve, that's just a simple on-off switch. A three-way valve is a bit more clever. It can send pressure to a device and then give that pressure a path to escape or exhaust. But the four-way valve, that's the real workhorse in automation. It can actually reverse the flow, which means you can use it to both powerfully push and powerfully pull a single component. So where is all this pressurized flow actually going? It's all heading to a cylinder. This is the component that finally turns all that carefully directed pressure into useful, powerful work. This is the bicep of the system. It takes all that pressure and creates a really strong, controlled push or pull. Okay, so we know these cylinders get their power from pressure. But pressure of what? And that question leads us to the two competing giants in the world of motion, hydraulics, which uses fluid, and pneumatics, which uses air. And right here, you can see the fundamental difference between them. Hydraulics uses oil, and oil is incompressible. You can't really squish it. That gives it just immense strength and rock-solid precision, perfect for heavy lifting, like a giant construction excavator. Pneumatics, on the other hand, uses air, and you can compress air. This gives it a kind of cushioned or springy quality. It makes it much faster, but not nearly as forceful, which is ideal for all those quick, repetitive tasks you see in a factory. A hydraulic system is totally self-contained. It's a closed loop. You've got a tank of oil, a really powerful pump to create intense pressure, and these super reinforced hoses to contain it all. The valves act as the brains, telling that power where to go, and the cylinder provides the muscle. It's an incredibly powerful setup, but yeah, it can often be pretty messy and noisy.
And when we say high force, we are not kidding. Hydraulic systems are routinely operating at thousands, literally thousands of pounds per square inch. That is just a mind-boggling amount of power, enough to lift many tons without even breaking a sweat. Pneumatic systems are a whole different world. They just use the air that's all around us, so there's no need for a messy oil tank. This makes them incredibly fast, lightweight, and clean. And they operate at much, much lower pressures. We're talking maybe 85 psi compared to the thousands you see in hydraulics. This is a system that's built for speed and agility, not for brute force. Okay, we have looked at all the individual pieces of the puzzle. Now, let's put it all together and see that full chain of command in action, from start to finish. And there it is, the entire process, from that first spark to the final force. First, a low-voltage electrical signal is sent to the solenoid. Second, the solenoid acts as a switch, giving a small, quick physical push. Third, that little push moves a valve, which acts as a gate, redirecting a massive flow of high-pressure fluid or air. And finally, that flow rushes into the cylinder, creating the powerful linear force that moves the machine. From a tiny spark to immense power, all in the blink of an eye. So, the next time you see a factory robot whirring around, or a big piece of construction equipment, or even just hear that solid thunk of your car door locking, you'll know the secret. You'll see that invisible chain of command playing out, the solenoid, the valve, the cylinder, all working together in perfect harmony. What other machines are you going to see in a completely new light now?